Good afternoon, everyone. Myself, Raka Mondal. I would like to start the second session with me today. So, this session or this lecture is about the hydrogen energy and the membrane that is used for hydrogen generation. So, in this session, we are going to learn about the types of membrane that we can use for this technology. We are going to talk about the different applications of specific membranes in specific hydrogen production technologies. How do we choose the properties and how do we analyze these membranes? The state-of-art membrane technologies, cost and efficiency analysis, and some industrial case studies. Hydrogen. It is not only a crucial form of energy, crucial form of fuel for production of energy, but also it is used in different parts of industry for different production purpose. It is used in fuel cell as a fuel to generate energy. It is also used in petroleum refining, ammonia production, and importantly, the most important contribution for hydrogen is that it is a clean fuel source. The hydrogen production methods include steam methane reforming, which is the most common used industrial method till now. It uses natural gas to produce hydrogen. We can also have electrolysis where the electrical energy is used to degrade or to degenerate the water molecule, and in that way we can produce hydrogen and oxygen. We can also have biomass gasification where the organic materials are converted to generate hydrogen. Photocatalysis, which is having a very good research focus nowadays, it uses sunlight directly to have the lysis of oxygen water molecule to generate hydrogen and oxygen. Membranes play a very crucial role in all of these production methods. They not only enhances the efficiency, it reduces the overall cost, it improves the purity level of the hydrogen, which is a very important. It controls the emission of greenhouse gases and it can contribute to a sustainable future. Now, with the method of hydrogen generated, the hydrogens are divided into three main categories. First is the grey hydrogen, which has been most widely used till now, which I was telling that it uses natural gas mostly, basically fossil fuel is used. So as a result, what we see is that we see a lot of CO2 generation. So it is carbon positive, that means we are generating or we are emitting carbon towards the environment. So it is not very environmental friendly or sustainable process. But what we have now is that our focus is slowly shifting towards blue hydrogen, where the carbon dioxide is stored underground. So these are either underground or any other CCUS method or carbon capture and storage method. So what we are doing here is that we are not emitting the carbon dioxide directly to the environment. So that is why either it is carbon neutral or it is not carbon positive, or carbon footprint is much lesser for blue hydrogen generation. Whether in green hydrogen production, we do not have any CO2 generated. So it is a most convenient or most sustainable process we can have. But in order to have a large scale production of green hydrogen or to shift our entire hydrogen production towards the green hydrogen production, we need a lot of research focus. Now, let us say what are the typical membrane based hydrogen production technologies. In membrane reactor, we can produce hydrogen where the membrane in the reactor, it acts as a medium for reaction, it provides a surface area, it also acts as a it enhances the selective transport in the through the membrane. So in our first lecture, we learned a lot about the transport mechanism through these membranes. So most of these principles of transport through these membranes are applicable in this type of membrane also. We also have PEM, or the proton exchange membrane, which is mostly used in the electrolyzers and the fuel cells of PEM category. So what does it do? It carries the hydrogen from the anode side to the cathode side, but also does not let the hydrogen and oxygen mix. We have to keep in mind, if the hydrogen and oxygen mixes, there is a very high chance of fire or accident. Okay. So the flammable limit is 4%. So we cannot have more than 4% mixing of hydrogen and oxygen. So we have to have a membrane which is very efficient in separating them. Okay. Now we also have steam methane reforming, where the hydrogen, the membrane is used for enhancing the purity of the hydrogen. We also have WGS, or water gas shift reaction, where the carbon capture happens through the membrane. Okay. Now basically the role of the membrane in all these categories is transport, selective transport. So which to pass and which not to pass through these membranes, that is the most important thing. Okay. So that is how we can have a good efficiency of our process. Operating conditions also vary quite a lot based on the type of method that we are using, based on the conditions that we are using. So that way you can operate a membrane at a room temperature, like in PM you can operate up to 80 degrees centigrade with the conventional membranes, but in MCFC or SOFC, some special type of fuel cells, you can go up to 800, 1000 degrees centigrade. So it depends on the type of operation that we are using. Similarly, the composition of the membrane, that will also vary based on the production method. It is used in form of integrated into these fuel cells, like as it is being shown here. There are some high temperature fuel cells like MCFC and SOFC, where the metallic membranes are captured or sandwiched between the anode and cathode side, and we have selective transport of some ions. Okay. They operate at very high temperature. They are integrated here, this PEM or electrolyzer. Here we have integrated this PEM membrane between the anode and cathode, where it is efficiently blocking the intermixing of hydrogen and oxygen and also selectively transporting them. Now one challenge which is still remaining, which we need to address more to have a widespread applicability of these technologies, is that the membranes tend to degrade over a long time. So they have a limited lifetime. After that, these transport properties or this efficiency, that goes down. So we have to be careful about what is the lifetime of the membrane, and we have to have a more high lifetime, so that the process can be more economic. Okay. So the research is going on to develop advanced material, to develop more cost effective material. Now what are the different types of membranes that we use? The types of membrane, as I was telling about PEM membrane, that it is in PEM electrolyzers. We can also have different other types of polymeric membranes also. So as Professor Vedanpur was mentioning in the first lecture, that there are lots of options for polymers. That we can make membranes with. There are lots of variations with the polymers. But they are not only cost effective, they are moderately selective, but one disadvantage or one challenge, I should say, in the hydrogen production particularly, is that their selectivity is comparatively lower than the inorganic membrane. Whether we want the membrane to be more porous in liquid filtration, but in gas filtration or this kind of application, we need it to be dense, so that the intermixing does not happen. We can have inorganic membrane, and palladium based membranes is a part of inorganic membrane which has been most popular. What is palladium based membrane? Palladium based membrane is nothing but some membrane which is mostly made up of palladium, either some other materials is mixed with it, or it is solely made of palladium. What does it do? It converts the H2 form into the H plus form, and then it converts it or transports it through its one side to another side. That is the role of palladium. Now, it gives you very good efficiency. It gives you almost 100% separation of hydrogen and other gases. One challenge here with this palladium, it is that it is very costly. So, if it is costly, then a large scale production of palladium, it is limited. We have other options in inorganic membrane which are made up of ceramic, silica, zeolite, etc. We can keep in mind that inorganic membranes are very highly stable thermally, and mixed matrix membrane, whether they are stable but they are not very highly cost effective, but mixed matrix membrane, it actually what does it do, or mixed matrix membrane or the composite membranes, it joins the goodness of these two. It joins the goodness of polymeric membrane and the inorganic membrane. So, it can be more scalable. So, where we are infusing some inorganic material into the organic matrix for mixed matrix membrane, it is making the membrane more porous but more selective at the same time, and also it is making it more cost effective, so that we can go for more scalable approach, more application in the real life. So, that is why many researchers are mostly focusing on this mixed matrix membrane, or what we call it as a composite membrane in general. So, if we look into the polymeric membranes, one of the type of polymeric membrane that is very popular is glass polymeric membrane. It is mainly thin film composite membranes are of this category. So, they are not in particularly thermodynamic equilibrium, so they are very rigid in structure. So, they offer very high selectivity compared to the other conventional polymeric molecules. They are very thin, they offer very high rigidity, very high selectivity. They are very dense in nature. And also there are other types of polymers like rubbery polymers. So, we have learned a little about the polymers like PSF, like SPEAK, these kind of polymers. They are rubbery polymers. They have comparatively higher permeability. They are more flexible, they are more economical, but they will have their particular advantage and particular challenge also. Mixed matrix membrane can be a mix up of organic and the inorganic molecules. Where they are particularly advantageous? They are particularly advantageous in PSA type application. It is pressure swing adsorption. So, in the membrane separation unit, the energy demand can be comparatively lowered. It is again applied together with fuel cell, refineries. It can be effective in separation of the hydrogen with the syngas and biogas for different hydrogen generation method. It is low cost and lightweight. It is highly scalable. It is also energy efficient because it is more permeable than the more denser membranes. The limitation or the challenge is that we need to improve the selectivity. We need to improve the sensitivity towards temperature. It should be more stable at higher temperature also. So, research is going on into that direction only. Now, what is PM membrane? PM membrane, as I was telling that PM membrane this is a typical structure of water electrolysis. So, what we are seeing here is that we have given the water molecules towards the anode side, and with this catalyst anode, what it is producing, it is that it is producing some protons, and in these protons is transported towards the cathode side, and there it is reacting, or this is getting the electron from the cathode side and generating hydrogen like this. In the anode side, the oxygen remains and the unreacted water remains, and it goes out. So, this oxygen and this hydrogen can be effectively separated by the membrane. At the same time, they should effectively transport the hydrogen molecules, protons, so that they should not be the rate limiting step in this whole case. The main advantage of this is that they provide a very compact design. So that's why we will find a lot of application for PEM technologies in transport sector, in car, in our space station. So there are a lot of application for PEM membranes. They offer very high efficiency, 75%, 85%, but they do not have a very high energy output. So we cannot give it or use it for a grid generation, grid electric generation. Okay. The main type of membrane that we use is PTFE. The commercial name is Mafion, and it gives you proton conductivity around 120 millisiemens per centimeter at 80 degrees centigrade, but what it does is that above 80 degrees centigrade, its conductivity goes down. So we can use some catalyst to improve the efficiency, but at the same time losing the cost effectiveness. It can give you very high purity oxygen. Okay. So when we combine this PEM technology or this electrical current source with a renewable power source, it really becomes very green technology in nature. Now, the inorganic type of membranes, they are made of palladium alloy or other metal membranes like nickel, vanadium, etc. They are very highly stable, high temperature operation can be done with this inorganic membrane. So here mainly hydrogen gas dissociates, proton diffuses, and this gives you a very high purity. So you can use it for SMR, steam methane reforming, water electrolysis, ammonia cracking, etc. It is very common in fuel cells, especially the high temperature fuel cell like MCFC and also SOFC, etc. We can have the advantages of this is that it gives you very highly selective, very high purity. It is more durable than your polymeric membranes. It is compact, it can be made compact, which is not as small in size in PEM, but it is highly engineering or tailoring of its structure can be done with this. But it has a drawback of, or not drawback, the challenge of a high cost, and it can be fragile at some selected situations where there is poisoning by carbon monoxide or sulfur like this. Now, why palladium? I was telling that palladium has been most popular among the all different types of hydrogen membrane. Why? Because it gives you, it can operate at a normal temperature of 300 to 600 degrees centigrade. So remember that if you need very high temperature for your membrane to operate, then you are losing the energy efficiency. You need high amount of energy to increase the temperature. So if it can operate in that particular range 300 to 600 compared to other inorganic materials which requires even higher temperature, then it is a plus point for palladium. Now its permeability is also very good, but one challenge is that it is very sensitive to sulfur, and also it is very expensive. Possible enhancement can be by introducing some other materials, by making alloy like silver, copper, etc. alloy can be made, so that the cost effectiveness goes higher, and also we do not lose the permeability. And next I will come to next type of membrane, that is a ceramic membrane. So what is ceramic material? Ceramic material are even made up of some particular components which are highly temperature stable. So what does it do is that they work at very high temperature like more than 500 degrees centigrade. It does not, so it gets activated at more than 500 degrees centigrade. It selectively transport the hydrogen. It can be engineered very effectively, like here I am showing, here they are showing some ceramic materials in a magnified situation where you can see that the pore structures are very uniform. This is one advantage of inorganic or ceramic membranes. The pore structures it can be made very uniform, which is normally usually very difficult in polymeric membrane. So now the advantage is that it gives you very high temperature sensitivity, it is resistance to chemicals, it is highly durable, and it stays on for a very long time. Now composite membrane can be made up of polymer and metal, ceramic and polymer, or can be mix up of all these three, or can be any types of, they are generally we call them different types of composite membrane, where the mixed matrix membrane is a subset of a composite membrane. The working principle, what is the advantage of this kind of composite membranes? That I was telling that it is adding up the goodness of the polymer and the inorganic also. So what we can have its application in different, we can have it as a different layers. So we can have a layer of polymer, on top of it a layer of inorganic, or either way, other way around, inorganic and then polymer, or we can have, which is the layer by layer assembly, we call this a layer by layer assembly, or we can have it infused, the inorganic material can be distributed towards the membrane. Even there is a possibility that you can make throughout the, so let us say that this is my membrane thickness. So I can selectively concentrate some inorganic material towards the one side. So let us say that I am concentrating some palladium nanoparticles towards one side of my membrane, polymeric membrane, so that they will offer the sensitivity towards the anode transport, towards the hydrogen transport, towards the transport through the membrane. So based on the gradient of mass transfer, based on the gradient of potential, you can decide which way to concentrate your inorganic material more. So that's why they are called very highly tailor-made. They can be very highly tailor-made. They can be very useful in some specific application. So advantage is that they are cost effective, because they are not using too much of inorganic material, they are cost effective, they are having very high thermal and chemical stability, they are highly selective compared to normal mixed matrix or very high open pore membranes, they are more selective. But one problem is that their manufacturing process needs to be simplified to have it very high large scale application. One problem, another problem that we have been learning about, that Professor Vatanpur works extensively on this, fouling of the membrane. So if we have fouling of the membrane, this transport property goes down. Now let us look into a little bit of the more conventional membrane, more conventional hydrogen production process, which is called the SMR, or steam methane reforming. In the steam methane reforming, what do we know? That our carbon monoxide and water, that is converted to hydrogen and carbon dioxide. That is basically the method of, that is basically the reactant and the product of SMR. Now in this process we need some catalyst, and if we can immobilize those catalysts onto a membrane, then what it is giving you is that it is giving you the immovable catalyst particles or more areas for mass transfer. So that is how you can enhance the total mass transport rate, you can enhance the reaction efficiency. So if the membranes are made up of, if the reactors features these membranes, they can also they can be also made to capture the carbon dioxide. How? So if you say, let us say that in my, I am using in a SMR, I am using a carbon dioxide capturing CCU, capturing MOF, or many other adsorbent for carbon dioxide capture, so that it can act as a CO2 capturing mechanism also. So not only in transport, but it will also attract the CO2, so that you can shift towards the green carbonate from the grey side of the hydrogen. Now it works, these membranes, this reaction, they works at a very high temperature. So we need that kind of membrane. So that is why mostly ceramic and palladium membrane based membranes are used in this type of operation. We generally prefer not to have purely polymeric membrane. The membrane advantage, I told you already, the advantages are high purity, energy efficiency, lower carbon emission, but the challenge remains about the durability of the membrane, because this is a high temperature operation. Again, with a prolonged use, its transport property goes down. So that is why we need to have a cost reduction also. We need to focus more on a hybrid system. Okay. So, I have talked about the SMR, which I told that it is mostly grey, but grey produces grey hydrogen. So, but if we can engineer it in effective process, so that we can make it more carbon neutral, so carbon footprint can be reduced. But what is thought of a more greener technology is electrolysis. So, practically passing electric current through the water so that they can be dissociated. Now, whether this process is challenging, but one method that is very well used is that you have a liquid cell where these two anode and cathode side, they are separated like a diaphragm. Diaphragm is nothing but a special kind of membrane. Now, what happens is that these diaphragm, when we are providing more of a liquid environment, then they are seen to be because the pH is highly varying from one side to another side, because the electric current, they are seen to be degrade very rapidly. So that's why many people, they are focusing mostly on PEM or AEM electrolysis, where the membrane itself acts as an electrolyte. So their role is to transport these oxygen and these ions, and they are separating also the oxygen and carbon. So we are avoiding this extreme variation in the pH and the ionic variation, so that our setup can be more stable. Whether if we have a very high power output requirement, we can go for technologies like SOFC or MCFC, etc., where inorganic material or ceramic material, it can be a more preferable choice. Now, the working principle is that the membrane, they do not split the water molecules, they are just using the transport mechanism through them and the selective transport mechanism through them. Now, the challenge here still remains if we can use it for long term stability or for a higher temperature operation. Next, let us look into a little bit about very green technology, where no kind of there is very less probability of using CO2 generation. What we can do is that we can use a renewable source of energy like solar or wind to have the electricity generated and pass it through this electrolyzer setup, so that we can have this membrane, this hydrogen and oxygen generated. So practically in this setup, if we are applying external current and we get that external current from renewable energy, then like for photocatalysis energy like solar or this visible light, so then we make the membrane photocatalytic membrane, or make the process photocatalytic process. So the role of this membrane is to, they separate the hydrogen and oxygen, they go for ion conduction, they provide chemical stability, they provide more mechanical efficiency and energy efficiency also. The type of membrane that we use for this type of membrane is, the most common one is the Nafion membrane, or also we also use SPEAK. SPEAK is the sulfonated ether ketone, sulfonylated ether ketone. So what does it do is that it is more available than Nafion, but it also has sulfone groups. So what does it do is that, I'll just show you. So if this is the membrane, which is like on this side you have anode and you have cathode on this side. So it will have very small water channels through them, very small water channels through them. So water channels is basically made up of polymeric backbone, two polymers of polymeric backbone, and they have, the polymeric backbones are hydrophobic in nature. They have some side chains which are giving you hydrophilic nature, so that this region between the two polymeric backbones, they are hydrophilic zones, but they have a boundary which is hydrophobic. So that's why it is making some water channels, or it is transforming, or it is enhancing the vehicular transport through which the water molecules are carrying one of the H plus ions through them. So like this we make different kinds of water channels, and in speak we make these more hydrophilic zones, hydrophilic side chains more, and this material gives a very good structure of these water channels. Now this is also found in different types of membrane materials like Nafion or anion exchange membranes or PERL membranes, etc. So this is a general structure of the membrane. They have varying thickness, and because of this thickness they are also resistance, not only because of this thickness but the internal structure. Therefore this also, their conductivity, their stability, that varies quite a lot. Okay. So now we have talked about, till now what we have talked about is that different technologies through which we use membrane and generate hydrogen, different types of membranes, and what are their roles and their specific challenges. Now let us see what are the characteristics, or how do you characterize a membrane, how do you know this membrane is useful for you. For that the main characterization techniques are SEM, which tells you about the morphology, whether there is any uniformity or non-uniformity, or whether there is defect. So all those kinds of things can be analyzed through the SEM, high magnification images. It gives you a crystalline nature structure if you analyze it through a XRD. So if your membrane is crystallinity is good, then the resistance towards the ion transport is less. So that's why we need a good crystalline structure or stable crystalline structure in the membrane. FTIR, it gives you the exactly what kinds of side chains are there in your membrane, so that you can have a good idea that whether it is which type of ions it can conduct very efficiently. You can have AFM. AFM is a surface morphology it is giving you. So whether you need to have very low roughness onto your surface also, because if the rough surface is very rough, then the contact between anode and the membrane or the electrolyte, it is very poor. So it gives you additional resistance to your transport system. Okay. You can have gas permeability testing, as I was telling that gas permeability should be less. It should be selectivity, it should be highly selective of hydrogen over the other gases. It should be mechanically strong so that it this in the high pressure environment it can be stable. Thermal stability, it should be for ceramic membrane, should be very highly thermally stable. For durability we have chemical resistance. So we expose these membranes to different substances like H2S, CO, etc. steam for very long hours, like 1000 plus hours, and we see that what is the mass loss or what is the structure changes in the membrane. We also do cyclic changes. So we evaluate the membrane performance under varying pressure, varying voltage. So with these conditions, how the membrane is, how many cycles it can sustain. We do also aging tests. So with very long time, how long it is staying good. So with these are the mainly typical characterizations that we do for different kinds of such membranes. There are different standardization or certification that is available, whether this membrane is good for practical use. For that we have ISO standard, we have ASTM standard. Basically they are for gas permeability testing through the membrane. We also have DOE standard. For DOE has a fuel cell and hydrogen program which establishes the durability structure and efficiency benchmark of the membrane. Okay. As I was telling you about different membranes, they have different types of properties. So if you compare, the polymeric membrane gives you very high permeability, but the selectivity is comparatively lower, and this is basically a summary of what I have told you about different types of membranes. Operating temperature for the polymeric and inorganic is in that range, but the stability is very high for ceramic membrane, high for inorganic and metallic membrane, but moderate for polymeric membrane. Mechanical strength is low for polymeric membrane because it gives you more porous structure, but its chemical stability is moderate also. Thermal stability, it has got specific applications in some specific categories, but inorganic membranes, they are of it is stable, it should be highly stable in very harsh gases because they are they are being exposed to very high temperature, very high operation efficiency. But metallic membranes has a drawback of they are very highly sensitive to sulfur content, which is not a very good sign for a mixed gas analysis or mixed gas separation method. Now, if we have a cost comparison, I should not say cost analysis, in the comparison of cost, polymeric membranes are much cost effective. So they are giving you option for large scale application. Inorganic membranes like palladiums, they are expensive comparatively. Ceramic membrane, they are comparatively less expensive than palladium. Metallic membranes are also too much expensive, but mixed matrix membrane can be a bridge between them and they can reduce the cost while retaining the efficiency. So the challenges till now is thermal stability issue, high cost, selectivity membrane for this, and optimization it has to be done with these membranes. Okay. So we have some hybrid systems with the membranes, like we can have thermochemical or electrochemical process or biological process. So what are those? Basically biological process is where we have a membrane bioreactor, or I will give you some example that when we have a microbes immobilized onto the membrane process, not specifically for hydrogen production, but it is a very useful application for water purification technology. So we can have such kind of idea to be evaluated to hydrogen, but we have to find such microbes which are stable in that kind of environment. We can have PM electrolysis with 80 to 90% efficiency. So these are the solid oxide membranes and they have their typical applications for this. Okay. Next, I would like to talk a little about the nanomaterials, because nanomaterials, as we know that it enhances membrane permeability and selectivity by providing high amount of surface area, by giving you the good stability, but what it does, it reduces the material usage. So the total amount of palladium that you have to use, the total amount of inorganic material that you have to use, that is reduced, so that is why your cost is reduced. But at the same time, making of this material in a stable and highly effective format, that requires a complex processing. So what kind of nanomaterials are being used? These kind of material, these kind of membranes are basically nanomaterials being imparted into your composite membranes. So that kind of membranes I am now talking about. So where you have either a polymeric materials imparted in it, some nanomaterials in it. So what kind of nanomaterials you use? We can use graphene oxide. It enhances the hydrogen selectivity. We can use carbon nanotube. You can use MOPS. MOPS is a very popular choice nowadays for increasing the gas separation efficiency. It enhances the lifespan, which is a significant improvement over polymeric membrane. It enables operation at lower temperature, significant improvement over inorganic membrane, and reduces energy consumption, significant improvement over inorganic membranes. But a challenge or more research should be there on large scale production, as I was telling that the production process itself is a little complex. So that's why for industrial separation or industrial scale production of these membranes, we need a optimized technology for large scale process. So mostly when we talk about the composite membranes, this is the main focus of our membranes, that we should go on more towards the nanomaterial side, but should be also at the same time more stable. But let us see a little bit of industrial applications. So industrial application for hydrogen demand actually has already crossed by 2023 90 million tons per annually. So you can imagine the level of hydrogen demand that is there in all over the industries. PM has been deployed in 5 megawatt electrolysis plant with naphthalene based membrane. Ceramic membranes, it increases, it has been in use for in a lower scale separation, and future trends is that to have a scaling up of these membrane reactors for having a more green hydrogen production. The standards that we have for these type of membranes is that we should have a ISO 14687 for purity standard, for industrial use ASME B31.12 for pipeline, and for semiconductor industries very ultra pure hydrogen is required for this portion. But membrane efficiency, it needs a higher selectivity, so for that palladium is there, and operating conditions is that polymeric membranes for this industrial application, they operate at the 25 to 80 degrees centigrade. So what are the environmental factors that we should keep in mind? So palladium membranes, we should avoid sulfur. For pressure variation, we should, high pressure operation enhances hydrogen flux, but we need to keep in mind that prolonged use in very high temperature, very high pressure operation will make our membrane brittle. If we have any kind of membrane, this is true for any kind of membrane. But chemical exposure, for especially for typical mixed matrix membrane, if we have exposure to CO2 and H2S, it reduces its lifespan. But longevity for industrial scale, if we reduce by per year, we get the efficiency reduced by 5 or 10%, then it is not very good for industrial standard. So for sustainability purpose, we have to have layer by layer assembly or advanced coating and composite membrane reduction in order to have a more environmental friendly application. Temperature and humidity is a little bit sensitive because as I was mentioning about naphthalene membrane, that they cannot operate more than operate very efficiently at more than 80 degrees centigrade. Why? Because these water channels that I was telling you, they have very narrow constrictions. They require water molecules to carry the hydrogen ions. So hydrogen H plus ions. Now in this case, if we do not have sufficient level of hydration, what will happen? There is no water molecules, so they will not be able to carry out the H plus molecules. So you need to have moderate level of humidity maintained. 80 to 100% humidity is very good for this kind of membrane. Okay. And for polymeric membrane also, if we have polymeric membrane, if we have more than 100 degrees centigrade, this naphthalene type of membrane loses its structure, this water channel they collapse. But if we go very high temperature, obviously the polymeric molecules they degrade at that much high temperature, they cannot sustain that much high temperature for this case. So we have to be careful about temperature, humidity, gas impurities, pressure variation, chemical exposure, and we have to check whether the longevity reduction is in a sustainable limit. So let us talk a little about how the hydrogen, carbon capture and hydrogen co-production can be achieved by this kind of composite membrane. So I was telling that we can impart some adsorbents for carbon dioxide into the membrane so that they can allow selectively hydrogen to pass through. Carbon dioxide, when it tries to pass through the membrane, they will be absorbed by these absorption processes. Okay. So the energy efficiency will be very high because we are also integrating two processes of carbon capture and hydrogen separation at the same time. We can have polymeric materials like PPAX, Matrimid. These are some commercial names. Inorganic membranes like palladium membrane based or MOF based or this kind of triple material for this kind of application. How do we know that our membrane is working properly? If we have carbon capture up to 85 to 90%, it is possible. So then we can use this membrane for our industrial application. But we have to be conscious that if our main membrane material is polymers, then we cannot operate more than 330 to more than 100 degrees centigrade operation. And if our main material is ceramic or inorganic, then we can go up to 400 to 800 degrees centigrade. What do I mean by main material? That is, if I have polymer as a main material, then the inorganic is infused in a polymeric matrix. So then we can go up to 100 degrees centigrade. If the inorganic is main material, then the nanoparticle or the polymeric particles, they are infused into the inorganic material up to 800 degrees centigrade. So we have to have a good trade-off between permeability and selectivity, and we have to have good membrane stability, and we need to have a hybrid system for this kind of material. I have already covered this information that we can have MOF, graphene or palladium alloy for composite membrane composition material, and we can also have mixed matrix membrane like zeolite, silica, etc. into the system. So for standardization, we can look for ISO 16100 2018 for safety standard. For standardization methods are on various aspects, not only on the purity level, but also on the safety level, the permeability and gas separation purposes. We have our DOE target, DOE or the Department of Energy. They have given a target that the membrane cost should be less than $200 per meter square, and hydrogen recovery more than 90%, and the durability of more than 5 years, so that we can have our composite membrane applicable in the industrial sector. So like this, there are some standards or the metrics that we should look for if we develop a new composite membrane and want to emphasize or extend it for industrial standard. So next coming to the safety consideration. So I was mentioning that hydrogen is very flammable, so we cannot allow absolutely no intermixing. We cannot allow any absolute intermixing between the hydrogen and other gases. So that's why if we have any exposure in the hydrogen, so it should be in the 4 to 75% range. If it is mixed hydrogen in the air, it is flammable. It will catch fire. So we have to be very careful about the hydrogen leakage. There should not be any defect in your membrane. There should not be any cracking in your membrane during the operation, so that you can be absolutely sure about there is no leakage happening inside this membrane. In this case, palladium membrane has stood the test of time. Pressure handling, membrane can be in such a way that it can handle up to 30 bar of pressure. Okay, 30 bar is a very high pressure limit, but why we have this thing in mind that it should be if there is a very momental variation in the pressure, in that any accumulation or coagulation or anything is there inside the membrane, it should not leak, it should not break. So that's why it should be able to handle 30 bar of pressure. Thermal stability for ceramic membranes, they should be at least stable in their TG value should be very high, so that it can be stable at 300 to 600 degrees centigrade. It should not lose its mass at sulfur and CO concentration, and these are the standard regulations for the safety consideration for this case. Now let us see if there are any industries which benefited by application for membranes in the energy sector. So now there is one product called PRISM membranes. They use membranes to recover hydrogen from refinery off gas. They have got hydrogen of 90% plus efficiency. They have got 30% energy savings by improvement over PSA method. There is shale and Evonik Separfan technology. They use it for biohydrogen production. It provides more than 98% purity, which is very considerable, considerably very high in this technology. We have high-gear hydrogen generation system, which employs palladium-based membrane for on-site hydrogen purification. We have IT-empowered electrolyzer with PM membrane used for green hydrogen production. We have DOE supporting the ammonia cracking method, which gives you very high purity standards. So there are different types of membranes that are offered in this scenario. Okay. Next, I am showing in this slide that how the membrane assisted technologies how they are performing compared to other technologies. Like say, if we have only PSA is an important tool for absorption-based gas separation system, which is pressure swing absorption. We can see that in all the technologies are sufficiently developed to give you almost 100% purity level, but energy consumption in membrane separation it becomes very low. Okay, compared to 2 to 5 for PSA and for electrochemical separation 50 to 55 kilowatt-hour per kg of hydrogen produced. So that way membrane separation, if you are assisting using membrane for this separation, it will give you very high energy efficiency. You can operate, you can vary it at different temperature. You do not have very strict pressure requirement or strict range, narrow range of operating pressure, and the cost is also very low if we compare it, especially with metal hydride separation or electrochemical separation. The cost is because of the material cost only, capex cost, we have very low amount of cost separation. So what are the emerging trends? So what should we look forward to for our more widespread application of this technology? We should have more advanced membrane materials for which the researches are going on. We should have electrochemical method, hybrid method applied to this membrane separation, size-based selective transport. We can have cryogenic separation also, so that we can have cryogenic separation is what we are using these in a very low temperature. So we are liquefying our hydrogen. So that if we can use the liquefying efficiency, that only will enhance the overall process efficiency of when it is assisted by membrane. There is a very high shift towards the AI process. So if we know that from the AI analysis, if we know that which combination deals with the best operating condition, gives you the best efficiency, then we can identify the particular operating conditions for the maximization of the efficiency for our site. We have a huge market growth. So if we can show this, or if we can establish this markers for our performance of the membranes, you can have a very high growth rate of the market. In fact, EU is targeting 40 gigawatt-hour electrolysis by 2030. Even our Indian government has taken up some efficient mission like natural green hydrogen mission, so that we can use or we can focus more on this membrane-based technology, hydrogen production technology for this section. So we should focus more on the AI, more on hybrid, and we should have scalable application. So now, why this scalability is important? Now, membrane in general is a very scalable technology. So it can be very highly, very easily, not very easily, there is established technology which can aid you to go from lab scale to industrial scale. But not everything goes proportionally. So if you have a 10 times more membrane area, you are not guaranteed to get a 10 times more lifespan. You are not guaranteed to get a few more properties. So what is the particular flux you are going to get? What is the particular permeability you are going to get? That is a research, or that is a physics-based system. We need to have more focus onto this, so that we can be more knowledgeable about how to go for the small scale from the lab scale towards the industrial scale. So that's why also we have to be more careful about the techno-economic analysis. If we are not giving any cost-effective solution, it is bound to fail. You cannot have a very widespread application. So that is all that I had to talk about different aspects of membranes for hydrogen generation. What are the take home messages? That it is very important, membranes play a very role from conventional to latest technologies. There are different types of membranes. We learnt about polymeric membranes, their specific properties, metallic, ceramic and composite membranes. And we learned about the membrane technologies, how they work in different processes like membrane reactor, PEM, WGS and SMR. We learned about their challenges and where the research focus lies in. We have learned about some industrial applications, future trends. We have learned about their standardization method, the safety standards, regulation and initiatives by the government. So that's what we talked about, and so I am happy to answer your question now if you have any question. Thank you. So any question on the audience side? So if there is no question, so there will be a short break of 5 minutes and then we'll proceed to the next session. Thank you.